Dear friends, today we will discuss the Neotectonics, active faults and geomorphological indicators. Neotectonics concerns the study of horizontal and vertical crustal movements that have occurred in the geologically recent past and which may be ongoing today. Though most crustal movements arise directly or indirectly from global plate motions, that is tectonic deformation, Neotectonic studies make no presumption about the mechanisms driving deformation. Consequently, movements is a vague catch-all term that encompasses a myriad of competing deformation processes, such as the gradual pervasive creep of tectonic plates, discrete or seismic displacements on individual faults and folds, and distributed tilting and warping through isostatic readjustment or volcanic upheaval. The phrase geologically recent past is also appropriately vague. Early attempts to define the discipline by arbitrary time windows, for example late Cenozoic, Neogene or Quaternary, have given grounds to a more flexible notion that envisages neotectonism starting at different times in different regions. The onset of the neotectonic period or the current tectonic regime depends on when the contemporary stress field of a region was first imposed. For instance, the current tectonic regime began in the middle Quaternary, that is 700,000 years ago in the Apennines of central Italy, and even more recently, that is 500,000 years ago. In California, in contrast, in eastern Northern America, the present day stress regime has been in existence for at least past 15 million years. Typically then, new tectonic movements have been in operation in most regions for the past few million years or so. Over such prolonged intervals, new tectonic actions are revealed by the stratigraphic buildup of sediments in the inland and marine basins, the burial or exhumation histories of rocks, and the geomorphological development of landscapes. Geological studies of paleobotany and paleoclimate, numerical models of landscape evolution, and techniques such as fission track analysis and cosmogenic dating are among the disparate tools unraveling this long-term tectonic activity. Over periods of many tens to several hundreds of thousands of years, the actions of individual tectonic structures, that is faults and folds, can be determined, unmasked by the deformation of geomorphic markers such as marine and fluvial terraces, and tracked with reference to the late Pleistocene glacial eustatic time frame. The apparently smooth deformation rates discerned over intermediate time scales are revealed to be episodic and irregular when faults and folds are examined over Holocene, that is 10,000 years. Over millennial timescales, secular variations in the activity of neotectonic structures can be gleaned from a diverse set of paleoseismological approaches, from interpreting the stratigraphy of beds that have been affected by faulting to detecting disturbances in the growth record of trees or coral atolls. Although new tectonic movements continue up to the present day, the term active tectonics is typically used to describe those movements that have occurred over the time span of human history. Active tectonics deals with the societal implications of new tectonic deformation, such as seismic hazard assessment, future sea level rise, etc., because it focuses on the crustal movements that can be expected to recur within a future interval of concern to society. Contemporary crustal movements may be discerned in earth surface processes and landforms, such as in the sensitivity of the alluvial rivers to crustal tilting. In addition, Geomorphological and geological studies are important in recording the surface expression of earth movements such as earthquakes, ground ruptures, which due to their subtle, ephemeral or reversible nature are unlikely to have been preserved in the geological record. However, active tectonics also employs an array of high technology investigative practices. Prominent among these are the monitoring of ongoing earth surface deformation using space-based or terrestrial geodetic methods, that is tectonic geodesy, radar imaging, that is interferometry of ground deformation patterns produced by individual earthquakes and volcanic unrest, and the seismological detection and measurement of earthquakes, that is seismotectonics. These techniques are applied globally via a worldwide standardized seismograph network and regionally via local seismographic coverage. The modern snapshots of the tectonism can be pushed back beyond the 20th century through the analysis of historical accounts and maps to infer past land surface changes or to deduce the parameters of past seismic events, that is historical seismology. In addition, earthquakes can leave their mark in the mythical practices and literary accounts of ancient people recorded in the stratigraphy of their site histories and in the damage to their buildings. Coming to the archaeoseismology. The time covered by such human records varies markedly, ranging from many thousands of years in the Mediterranean, Near East and Asia to a few centuries across much of North America. Generally, records confirm that regions that are active today have been consistently active for millennia, thereby demonstrating the long-term nature of crustal deformation, but occasionally records reveal that some regions that appear remarkably quiet from the viewpoint of modern seismicity, such as the Jordan Rift Valley, are capable of generating large earthquakes. In reality, the distinction between neotectonics and active tectonics is artificial. The terms simply describe different time slices of a continuum of crustal movement. This continuum is maintained by the persistence of the contemporary stress field, which means that inferences of past rates and directions of crustal movement from geological observations can be compared directly with those measured by modern geodetic and geophysical methods. Although the term neotectonic and active are somewhat blurred and are often used interchangeably, societal demands, for instance regularity, or authorities for seismic hazard, nuclear safety, etc., often require the incidence of tectonic movements to be defined strictly. For instance, in the United States, under California law, an active fault is presently defined as the one that has generated surface rupturing earthquakes in the past 11,000 years. That is, the time period was established to relate to the time when the Holocene was considered to have begun. Other regulatory bodies recognize a sliding scale of fault activity, Holocene activity in the past 10,000 of years, late Quaternary, that is activity in the past 130,000 of years, and Quaternary activity in the past 1.6 million years. Neotectonism or faults, by comparison, are simply those that are formed during the imposition of the current tectonic regime. Real structures, of course, are unconstrained by such legislative concerns. Many modern earthquakes rupture along older, that is paleotectonic basement faults. Indeed, it is important to recognize that any fault that is favorably oriented with respect to the stress currently being imposed on it has the potential to be activated in the future, regardless of whether it has moved in the geological recent past or not. A useful way to differentiate styles and degrees of neotectonic activity is in terms of tectonic strain rate, which is a measure of the velocity of regional crustal motions and in turn of the consequent tectonic strain buildup. Crustal movements are most vigorous and therefore most readily discernible where plate boundaries are narrow and discrete. In these domains of high tectonic strain, frequent earthquakes on fast moving, that is more than 10 millimeters per year faults ensure that a century or two of historical earthquakes and a few years of precise geodetic measurements are sufficient to capture a consistent picture of the active tectonic behavior. Intermediate tectonic strain rates characterize those regions where plate boundary motion is distributed across a network of slower moving, that is 0.1 to 10 millimeters per year. Examples of such broad deforming belts are the basin and range province of the western United States or the Himalayan collision zone, where earthquake faults rupture every few hundred or thousands of years, ensuring that the Holocene period is a reasonable time window over which to witness the typical crustal deformation cycle. In contrast, areas with low strain rates ensure that intraplate regions, often referred to as stable continental interiors, are low seismicity areas with slow moving, that is less than 0.1 millimeter per year, faults that rupture every few tens or even hundreds of thousands of years, making the snapshot of human history an unreliable guide to the future incidents of tectonic activity. The global pattern of present-day crustal motions can be accounted for by plate tectonic theory, that elegant kinematic framework in which rigid plates variously collide, split apart, and slide along their activity deforming boundaries. Closer inspection, however, reveals that the basic rules that govern global plate motions, that is, rigid blocks separated by narrow deforming boundaries, break down at the regional and local scales. This is particularly so on the continents where a patchwork of pre-existing geology and structures ensures that tectonic stresses are not applied in a uniform, straightforward fashion. Studies of how the contemporary stress field varies across Earth's surface distinguish between first and second order stress provinces. First order provinces have stresses generally uniformly oriented across several thousands of kilometers. The largest of these are the mid-plate regions of North America and Western Europe, where the stress fields are largely the far-field product of ridge push and continental collision. In contrast, first-order stress provinces in the tectonically active areas are dominated by the downgoing pull of subducting slabs and the resistance to subduction. Second-order stress provinces are smaller, typically less than 1,000 kilometers across, and are related to crustal flexure induced by thick sequences of sediments and post-glacial rebound. And to deep-seated geological contrast, although the bulk of Earth's crust is in compression, significant regions of extension occur in both the continents and the oceans. These extensional domains are long and narrow and correspond to topographically high areas, though notably exceptions are basins and range provinces and the Aegean regions of the eastern Mediterranean. Most first-order stress provinces and many second-order stress provinces coincide with the distinct physiographic provinces. Coming to the glacial isostatic adjustments, plate driving forces may exert the dominant control on the contemporary stress field, but another process contributes to the crustal deformation at a global scale. That process is glacial isostatic adjustment, and GIA for short. the physical response of Earth's viscoelastic mantle to surface loads imposed and removed by the cycles of glaciation and deglaciation, to which the planet has been subjected for the past 900,000 of years. Because large ice mass fluctuations induce the subcrustal flow of material, measurable crustal deformation extends for thousands of kilometers beyond the limits of the former ice margins. Consequently, the effect of GIA are felt globally. In addition to the crust's elastic response to ice sheets decay is geologically immediate. The delayed viscoelastic response of the mantle ensures that GIA can persist long after the ice has gone. Although the effects of GIA can now be detected from space geodesy, its legacy is most clearly visible in the worldwide pattern of post-glacial sea level changes. Regions that were ice-covered at the last glacial maxima, or LGM for short, are uplifting, that is, relative sea level is currently falling as a consequence of post-glacial rebound of the crust. Likewise, the regions of peripheral to the former ice sheets are subsiding, that is, relative sea levels are rising due to collapse of the glacial forebulge. The effect of this subsidence outside the area of forebulge collapse to its drawing water from the central ocean basins, which is compensated by uplift in the ocean basin interiors in the far field of the ice sheets. The final GIA component is the hydroisostatic tilting of continental coastlines due to the weight applied to Earth's surface by a returning meltwater load, which produces a halo of weak crustal subsidence around the world's major land masses. For the most part, geological studies of Holocene relative sea level changes are consistent with the uplift or subsidence pattern predicted by the global viscoelastic theory. The key areas of misfit are along the plate boundary seaboards, especially subduction zones where tectonic deformation dominates, and those areas contaminated by local anthropogenic effects, groundwater extraction, etc. The neotectonic implications of GIA are not confined to the coastline. Glacial rebound is now widely considered as an effective mechanism for exerting both vertical and horizontal stresses, not only within the limits of the former ice sheets but for several hundred kilometers outside. Within the former glaciated parts of the eastern North America and northern Europe, both tectonic and rebound stresses are required to explain the distribution and style of both postglacial and contemporary seismotectonics. Outside in the ice-free forelands, predicted glacial strain rates are still likely to be 1 to 3 orders of magnitude higher compared to tectonic strain rates typical of continental interiors. Consequently, some workers argue that an apparent switching on of Holocene earthquake activity in the eastern United States and the occurrence of typically large seismic events such as the great magnitude Modenate earthquakes that struck the Mississippi Valley area of New Madrid in 1811 to 1812 may be associated with areas where glacial strain rates are particularly high. Glacial loading and unloading may also disturb the buildup of tectonic strain and glaciated plate boundaries, such as today in Alaska or previously when the Cordilleran ice sheets kept part of the Cascadia subduction zone. More recently, the isostatic component of glacier erosion in mountain building process is becoming appreciated. The worldwide patterns of vertical and horizontal crustal movements arise from the global effects of plate motions and glacial isostatic adjustment. Regionally and locally, this is augmented by flexure from eustatic or sediment loading, volcanic deformation or anthropogenic change, that is dam impoundment. Through many neotectonic investigations seek to disentangle movements arising from the imposition of tectonic strains from those augmented by neotectonic processes. This is often a fruitless holy grail because deformation of Earth's crust typically induces compensatory flow underlying the mantle. Neotectonic movements are applied globally. Nevertheless, the disparate contributory mechanisms coupled with the varying timescales over which their actions can be discerned ensure that neotectonics encompasses a remarkable breadth of research disciplines. Few other fields easily blend topics as disparate as a space science. Seismology, quaternary science, geochronology, structural geology, geomorphology, geodesy, archaeology, and history. It is this interdisciplinary marriage that makes neotectonics particularly exciting and especially challenging. Coming to the geomorphological indicators. The manifestation of the active faults or neotectonic activity is expressed by some peculiar geomorphic features. They include unpaired river terraces, tilted constructions like temples, etc., sudden change in river course, peculiar drainage pattern like trellis, escarpment, etc., unpaired rear terraces. In nature, the fluvial systems try to maintain the base level and usually the terraces made by them are symmetrical or paired. They may, however, be shifted or displaced due to neotectonic activity or some sort of an active fault. It is fairly common in lineament-controlled system of streams and rivers. Coming to the tilted constructions, the man-made constructions also show the expression of neotectonics in the affected areas. It may be seen as propagation of cracks in walls and windows of the buildings. Tilting becomes more conspicuous in the apex of temples and churches, etc. Next is the abrupt change in river course. If a river or stream suddenly turns at right angle to its main course, it is an unequivocal evidence of an active fault. Rivers meander, anastomose, or become braided usually, but when they encounter a plane of anisotropy like a fault plane, major joint, or a prominent shear zone, they follow a trend of deformation making abnormal surface expression. This becomes significant for mapping lineaments. Coming to the peculiar drainage pattern, the signatures of fluvial processes that are inscribed upon the landscape as branching patterns of stream channels and drainage divides are as different from each other as your and my handwriting. A few special kind of drainage pattern gives an insight of the neotectonically active terrain. The subsequent streams originate after the master consequent streams follow the axis of faults. A strike of beds are called as subsequent streams. They not necessarily indicate a chronological sequence, but a relation between a drainage on one hand and geology on the other, and have a tendency to explore belts of structural weakness due to soft strata, fault, joint planes, and shatter zones. For example, Asan River, a tributary of Yamuna, and Son River, a tributary of Ganga in Dehradun Valley, is subsequent streams. The antecedent streams, however, are those which are originated prior to the uplift of the land surface. In other words, these streams antedate upon the upliftment of an upland or mountain across which they have maintained their present course through continuous downcutting of the valleys. For example, the Indus, the Satluj, Ganga, Ghagra, Kosi, and Brahmaputra, etc. They are all antecedent to all the three ranges of the Himalayas, while outer, lesser and greater. Jhelum, Yamuna, Ravi and Ramganga are antecedent to only lesser and outer Himalaya, while Kamla, Rapti and Gola streams are antecedent to only outer Himalaya or Shivalik ranges. These streams, in case of superimposed drainage system, flows on the land surface, and as the time passes, the stream cut through and encounters the lower strata. The latter has no option than to adopt the previous course, in spite of either being folded or representing an unconformity. The stream is said to be superimposed on the underlying layer. For example, Son River cut Kinjua ranges, which underlies Riva Plateau and therefore represents superimposed profile. The trellis pattern is formed by those consequent streams which run parallel and are joined by lateral consequent almost at right angles. It also shows a fault affected area. In the rectangular pattern also, the streams meet at right angles like in trellis pattern, but in this case the stream spacing is wider. Rectangular pattern is commonly controlled by intersecting faults or joints. Now let us conclude the entire discussions. Earth movements in the recent geological past refer to a significant aspect of modern geology known as neotectonics. The surface expression of the release of stress manifested in the form of active faults, earthquakes, etc. can be even on a scale of human lifetimes. The activity of San Andreas Fault, for example, still causes earthquakes and modifies the landscape. Also, this kind of study gives a new framework to analyze the geomorphology and finally shines an insight as to why a drainage pattern is the way it is. Thank you very much.